In this video, I want to share with you some of the aspects of internal BGP as it exists within a single autonomous system within a service provider core network. In particular, I want to talk about some of the scalability aspects of multi-protocol internal BGP because with ibgp, there is a full mesh rule in effect, okay? By the way, throughout this video, I'll probably just refer to multi-protocol ibgp, which is the capability of internal BGP in the more modern day, is capable of carrying so many different address families. But to keep it short, I'll probably just say ibgp. And so about that full mesh requirement that ibgp has, what this is about is ibgp assumes that every neighbor is connected to every neighbor. Connected physically? No. Connected logically by neighbor sessions. These neighbor sessions are actual TCP layer 4 virtual connections, okay? And so ibgp assumes that there is a full meshing of every neighbor to every neighbor. This is because this is a loop prevention mechanism built into internal BGP so that when an ibgp speaker receives a route update from a neighbor, it does not ever forward that to another ibgp neighbor. This prevents loops. Because of this full mesh rule, it becomes an administratively burdensome task, an increasingly burdensome task as your network grows. So the more nodes you have, the more TCP neighbor sessions you will be required between your ibgp speaking nodes within your network. For a moment, I'll refer back to something I speak about in my service provider architecture videos, which, by the way, I'll link in the cards or the comments so that you can refer back to those, that within a network, you have high-level roles assigned to your nodes. In the service provider core, you either have a P or a PE node. In the customer side, you have a CE or a C node, but we won't talk about those for a moment. We're only focused on the service provider core. So the PE nodes are those nodes that are directly connected to customers. The P nodes are nodes that only connect to provider edge nodes. Okay, so in this diagram, you can see router 1, 2, 4, 7, and 5 are in fact the provider edge nodes. Those are the ones that have the bulk of the configuration regarding VPNs, as well as ibgp configurations. The router 3 and 6 don't need to have any VPN configurations because they don't ingress or egress customer traffic, nor do they need to have internal BGP configurations either. I remind us of these foundational truths within service provider architecture so that we can correctly focus our attention on where ibgp must be configured. That is configured on the PE nodes, 1, 2, 4, 7, and 5. These are the touch points for configuring the full meshing of ibgp. So to bring a little more focus on those provider edge nodes that require the ibgp configurations, you can redraw the architecture at a logical level. These are the nodes that will be needing to be full meshed with ibgp. The full mesh rule is n times n minus 1 divided by 2, n being the amount of nodes in the network. We have 5 nodes here, and so n would equal 5. This would be 5 times 5 minus 1 divided by 2. 5 times 5 minus 1 is 4 divided by 2. 5 times 4 is 20 divided by 2 equals 10. What this means is there are 10 connections to fully mesh this network. I'll remind you that these full meshing of connections are logical neighbor sessions from BGP speaker to BGP speaker. Everyone must connect to everyone to be fully meshed. Those are TCP port 179 BGP sessions. Let's visualize this by drawing lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's our 10 connections. So focusing on the scalability concerns with a sprawling or growing service provider core network, every time you add a node, you have to touch every other node to configure the return TCP session. So if we were to add another node over here, let's just insert another one, call it 8. You have to configure 5 sessions from here. 1, 2, 3, 4, 5. But you also have to configure the return session on 1. You have to go touch router 1. You have to touch router 2 to configure that return session. You have to touch router 4 to configure that return session. You have to touch router 5 to configure that return session. And you have to touch router 7 to configure that return session. So this just grows and grows. Also, with full meshing, you have BGP updates that are sent out every one of these sessions. So if router 1 has to send an update, it sends the update out this session, that session, that session, this one, and this one also. As well as all the other nodes are doing the same thing. The more touch points you have, the more chance of typographical errors that you have. And also, each session has a unique IP address that needs to be different. So every router's configuration is a little different than the other routers. And this is going to be a key point in scaling this environment in a moment when I emphasize the single configuration needed on these IBGP speakers. There are 2 ways to relax the full mesh requirement in IBGP: confederations or route reflectors. Route reflectors is a popular way of doing this in service provider networks of today. So we're going to go over the route reflector style. A route reflector takes routes learned from IBGP neighbors and reflects them or forwards them to other IBGP neighbors. Now you might be thinking, wait, hold on. I thought IBGP had a loop prevention mechanism whereby which it would not forward an IBGP update to another IBGP neighbor. Yes, that's true. But when you're configuring a route reflector, you define your IBGP neighbors as route reflector clients. This is how we forego or relax the full mesh rule, because now route reflector in the center sees these neighbor sessions as route reflector clients, and it thinks that those clients are not fully meshed to these other clients, so it needs to do its job and send an update from router 2 over to router 1, as well as 4, 5, and 7. And the same thing is true for any update coming from any other route reflector client. So the dotted lines represent the route reflector client sessions. Now, the route reflector can be any node within the service provider network. It can be a PE node or it can be a P node. Normally, the P node is a high-speed label switching node in your network that doesn't need any VPN or BGP configurations on it. Just purely segment routing or MPLS swapping function is taking place on a P node. But if you determine that you want to use a P node to be a route reflector, then you can do that. Okay? We're probably going to do that in the lab here. We'll use a P node to be our route reflector. And so it could also be a process that exists on one of your PE nodes. Okay, and logically you could still depict it like this just to show that the route reflector process does a certain function in the network, but it could exist on one of these other PE nodes. A lot of providers would like to keep that function separately to share load within the service provider architecture, okay, but you could implement it really anywhere. Now, one glaring problem here, single point of failure. If you catastrophically lose the node that the route reflector is implemented on, look what you've just done. BGP neighbor sessions from all of these edge nodes no longer have a neighbor to connect to. Okay, so you have just brought down your entire internal BGP architecture by losing one node. This is not good in a service provider environment where high availability and uptime is of utmost importance. Ah, that's better. I can sleep easier at night knowing that my service provider core network has redundancy. Less possible catastrophic outages affecting all of your customers now that you have a what is known as a dual route reflector hub architecture. So each PE node only has 2 BGP neighbor sessions, one to each route reflector. And then the route reflectors have a neighbor session to every other PE node. I also like to configure a normal ibgp neighbor session between the 2 route reflectors as well. So dotted line represents clients, solid line represents a regular BGP session. So now if you lose this node here, everybody is still connected. All your PE nodes are still connected through this other one. And if you lose that one, they're all connected through that one. All right, so this is a lot better. I'll also point out when adding address family capabilities to a neighbor session, the neighbor session will usually bounce. So if you've rolled out layer 3 VPN v4 address family in your network, and sometime in the future you roll out VPN v6 for doing IPv6 over your layer 3 VPNs, you need to implement 6VPE. And so you need the VPN v6 address family to run on these neighbor sessions as well. When you do that, the neighbor session bounces. If you have 2 neighbor sessions, a redundant route reflector architecture, then you could reconfigure this neighbor session with the additional VPN v6 address family. That neighbor session will bounce. However, this one is still up, so you're still learning your full tables from all your other PEs across that session. When this one bounces, you lose all of your routes that were learned on that session. But your router still has redundant routes on this other one. When this neighbor session settles down and it goes back to established after configuring VPN v6, and you see that you are now relearning all those routes on that neighbor session after it's come back up, you can then add VPN v6 to this other neighbor session and allow it to bounce and reinitialize and become established. So this is really good in being able to further support additional address families on your neighbors when you have those 2 redundant route reflector sessions. The originator-id BGP attribute and the cluster-id BGP attribute is now what is used in a route reflector environment. Those are the attributes that are used for loop prevention. So when updates are sent into the route reflector environment from an originator, that originator ID is carried into it. So that if a BGP speaker ever learns of a route with its own originator ID, it knows that that's a looped route and it'll drop that route. The cluster ID is another one. If a route reflector receives a route with its own cluster ID in it, it will drop that route knowing that it is also looped. Okay, so here's our lab, and let's look at this. Let me move myself out of the way. Here's our SP core, router 1, 2, 3, 4, 5, 6, and 7. And our CEs are out here, CE 1, 2, 3, 4, and 5. Here's the PE to CE subnets, 192.168.1.0/30, .4/30, .8/30, .12/30, and .16/30. And the way I've IP numbered these is, as is typical in provider networks, the lower IP is on the service provider side, So dot 1 is here and dot 2 is over here. And in this case, dot 13 is here on the PE and dot 14 is on the CE. So let's just go over to CE1 and let's check connectivity to all of these. Excuse me, 192.168.1. Let's start with the lowest number, CE3. That would be dot 6. Then CE5 is dot 10. Then CE2 is dot 14. And CE4 is dot 18. So we know that everybody is reachable in the layer 3 VPN. And so I want to stay on track. I don't want to get too far down in the weeds, showing things that I've already showed in other videos. Check out my other layer 3 VPN videos of multi-vendor, multi-operating system, of how to verify various things with routing and multi-protocol BGP, advertisements and the labels and things like that. But I want to stay on track with how the neighboring of BGP works in a full mesh and what we do to convert that to a route reflector architecture. So if you look at, let's start with router 1. We'll give an example of Junos. Here's our neighbors. And so coming from router 1, we should have a neighbor going to all the other PEs. Our PEs are 1, 2, 4, 5, and 7. So on router 1, it should be 2, 4, 5, and 7. And it is. There's 2, there's 4, there's 5, and there's 7. Show BGP summary, shows that we have 1, 2, 3, 4 established neighbors with 2, 4, 5, and 7. This is good. And so this is what we would expect. Let's look at XR. We'll look at router 4. Here is the show run router BGP configuration. We see 1, 2, 5, and 7. And show BGP all summary will show our neighbors 1, 2, 5, and 7. All right, that's XR, that's iOS XR. And here is iOS XE. Show run section router BGP. We see coming from router 7 that we have neighbors to 1, 2, 4, and 5. And show BGP all summary will show us our active neighbor sessions with 1, 2, 4, and 5. So this is the full mesh that we've been talking about, where everybody connects to everybody, and we see that all the PE's configurations are a little bit different because each set of IP addresses is different depending on what PE you're on. So we'll compare that to a route reflector configuration. Okay, let's look at one more thing before we convert this to a route reflector architecture. From the perspective of router 1, if we show route table and the name of our VRF, we can see the PE to CE/30 subnets that we're learning throughout the layer 3 VPN. It tells you from what PE loopback IP address that it's learning these subnets from. Okay, from 10.10.02, 10.10.04, 10.10.05, 10.10.07 is the router 2, router 4, router 5, and router 7 loopback address that we are learning these subnets from. Now, also, if you look at the details and you grep for proto, you also see that the protocol next hop is the same as the routing table shows of where it's learning those from. And I want to show you how that differs when you get into a route reflector configuration. Okay, I mentioned earlier that I was going to show a dual hub route reflector configuration using two vendors cooperating together to form the redundant route reflector dual hub architecture. So we have router 6 as iOS XR. We have router 3 as Junos. Okay, the configurations are going to look like this. For Junos, first we set the AS number, and then we set up that vanilla ibgp session to router 6, the box, the iOS XR box. But then we have a different BGP group where we set the cluster ID and then All the neighbors under this cluster ID configuration are now known as route reflector clients. So there's router 1, 2, 4, 5, and 7. And the other route reflector on router 6 running iOS XR looks like this. We set the BGP cluster ID, and then the neighbor back to the Junos box, router 3, is a regular BGP neighbor. But then we set up a neighbor group and we specify the settings that are common to all of our neighbors, router 1, 2, 4, 5, and 7. And one of the key configuration items in iOS XR is you, under address family VPN v4 unicast, you set route-reflector-client. Then when you configure each one of your neighbors, you call this neighbor group, my route reflector clients is what I named it. You call that neighbor group, and all of these settings take effect on all of these different route reflector client neighbors. Now, the route reflector client side configuration for Junos and iOS XR and iOS XE is shown here. What we're going to be doing is we're going to be deleting the full meshing of neighbors, and then we're going to simply replace that with a neighbor to router 3 and router 6, our route reflector dual hub neighbors, router 3 and router 6. And this code can be reused in any Junos box that is part of our ibgp infrastructure, because we will always only neighbor with our dual route reflector hub. So iOS XR, similarly, we're going to be deleting our full meshing of neighbors, and we're going to be setting up 2 BGP sessions, one to router 3, one to router 6. Again, this is the same on every iOS XR PE in our entire network, because again, we're only neighboring to the dual route reflector hub, router 3 and router 6. Likewise, iOS XE, we are deleting our full meshing of neighbors and setting up neighbors to router 3 and router 6. Okay? And so let's put these configs in place and see them in action. And also, you may have picked up on the fact that the only mention of route reflector client in the configuration is on the actual route reflectors. When you're configuring the route reflectors, that's where the route reflector client logic takes place. So in Junos, it's inherent under the cluster ID command. If your neighbors are part of this group, this BGP group, all these neighbors take on the behavior. They're treated as route reflector clients, okay? And then the Junos box is reflecting routes to all these clients, okay? In XR, similarly, all the neighbors that possess these settings, particularly this route-reflector-client, all these neighbors will be treated as route reflector clients, meaning this XR box will likewise forward updates to other ibgp neighbors that are taken on the characteristic or this setting of a route reflector client. But when we get down into the actual router that is a client, when you configure that side, as I just showed you in Junos and XR and XE, there is no mention of route reflector client anywhere in these configurations. Okay, so it's on the route reflector side where the magic takes place. Let me correct myself real quick. Previously, I had shown when deleting BGP neighbors, after the actual IP address, I had the family iNet VPN v4 unicast. That would only delete that family, but it would leave the neighbor in place in the configuration. So in order to get rid of the neighbor completely, you need to do it like this. All right, let's put these configurations in place. For the first route reflector, router 3 running Junos, I'm going to paste this a little bit at a time. Sometimes the terminal emulator can't handle too much input at once. Okay, that's the first route reflector on router 3. Here's the iOS XR config for router 6. For the other part of our route reflector dual hub. Now let's do the clients. We are deleting our full mesh and then putting in the two route reflector connections. In Junos, we have router 1 and router 2, so let's do both of those. There's router 1, here's router 2. Okay, now let's do our iOS XR PEs, deleting our full mesh and putting in the two neighbor sessions to the route reflector dual hub. Router 4 and router 5 are running XR. There's router 4. Here's router 5. And then the iOS XE box, router 7. Let's get this done. We're already getting messages. Okay. Let's get right back over to our customer side and see from the perspective of CE1, can we ping 192.168.1.6, that's CE3, 1.10 would be CE, got off the screen a little bit there, CE5, excuse me, 1.14 would be CE2, and 1.18 would be CE4. So we can see that these are all reachable using this new dual route reflector hub. Let's trace route to some of these. 192.168.1.6. We can see our dual MPLS labels through the core and the VPN. Our dual labels. Okay. 10 was another one. There we go. Okay, let's verify what these BGP sessions look like. In Junos, on PER1 show BGP summary, we only have two neighbors, 3 and 6. These are our two neighbors to our dual route reflector hub. Let's look at PE2. We have two neighbors, 3 and 6. Oh, look at this. There's a leftover neighbor from when we were reconfiguring this. This is a perfect example of how, if you're not careful, when you have a full mesh, the configurations are different on every PE. Previously, I tried to set up a config script where I would delete a set of neighbors from the Junos boxes as well as the XR boxes. But what you're going to see is that we failed to realize that's not a same set of neighbors. Okay, so let's get into here and find out. So we need to get rid of that other neighbor. Our config script did not account for that. Let's get rid of that neighbor. Let's commit that. Show BGP summary. Excuse me. Now we only have two neighbors. We're going to see the same thing for router 4 and 5 XR. Let's go over here, show BGP all summary. Since our base config that we were using to create the XR configuration to convert from full mesh to a route reflector architecture was based on the first XR router, router 4, I'm thinking router 5 is going to have a leftover, neighbor. So let's see, show BGP all summary. It sure does. It's got a leftover neighbor. Show run router BGP. See, this is just a perfect example of you can't do code reuse very well when configurations aren't the same. And when you're going to a route reflector environment, all your PEs have the same configuration for the most part when they're, as far as their BGP neighboring goes, because they only neighbor to the same two routers that form the dual route reflector hub. So let's get rid of this other neighbor that we no longer need, which is 4.4 there. So let's say no to that neighbor. Show config. It's going to remove that neighbor. Let's commit that. Okay. Show BGP all summary. Now we only have two neighbors, .3 and .6, the same as router 4. Very good. And then router 7. Show IP BGP summary all. I think it's all. Oops, excuse me. All summary. There we go. .3 and .6. So now let's go look at our route reflectors. Show BGP summary in Junos. We have a neighbor 2.1, 2, 4, 5, and 7 are the clients. 6 is the actual other route reflector. Let's look at the other route reflector. Show BGP all summary. And we have neighbors for 1, 2, 3, 4, 5, and 7, and .3 is the other route reflector. Now looking at the route reflectors, show BGP neighbor and search with pipe grep, client, pipe peer, you can see that all of your BGP neighbors are clients, route reflector clients, except, so you see this one is, and this one is, and this one is, and this one is, except 10.10.06. That's our other participant in our dual route reflector hub. So that one is a vanilla BGP session. That's how you see it in Junos. Here's how you see it in XR. Show BGP all neighbors. Pipe include client, pipe BGP neighbor. And you see that all of your neighbors, all of your neighbors are route reflector clients, except when you look at this one, 10.10.03, that's going back towards the Junos box. Okay, let's go back to something that I mentioned earlier. In router 1, the Junos PE connecting to customer edge 1. Show route table in the VRF route table, 1.inet.0. You see the PECE subnets, the 192.168 address space that is using the VRF, but now you see there are actually two different BGP entries for each one of these subnets. Okay, there's one, there's another one. Here's one, here's another one. And it tells us that of these two BGP entries, the asterisk says asterisk equals both. It's the active route, it's also the last active route. So if we hit the up arrow and say active, it'll show us only that active route. Before I move on, look what it tells us about each one of these. This one is learned by 10.10.03. This one is learned by 10.10.06. This one is learned by 10.10.03. This one is learned by 10.10.06. .3, .6, .3, .6. So you'll remember from before our route reflector conversion, when we were fully meshed, we actually saw the remote PE loopback address in the from field for each for each /30 address that we were learning in the VRF. But now it shows the IP address of the route reflector. So it's a little bit harder to find out what the remote IP address is, but it can be done. And here's how. First of all, let me show you. If you show the same table with active path, you'll only see the active path. Okay, so 10.3, 10.3, 10.3, and 10.3 is the active path. Okay, now if you say details, well, there's going to be a lot of information for all these. So I just ran the screen really fast. But grep for protocol. Now look at that. Now you see who the protocol next hop is for each one of those. So that's for each one of those subnets. But if you wanted to find out, for instance, 192.168.1.8/30, Okay, let's look for only that subnet. 192.168.1.8/30 active path details grep proto, and you can, excuse me, I didn't spell it out all the way, and you can see 10.10.07 router 7 down here is where 192.168.1.8/30 is actually being learned. Let's look at a similar thing in iOS XR. Let's take router 4, for instance, this router right here that has CE3 hanging off of it. Show route table and the VRF table. Oh, excuse me. Show route VRF1. That's how you look at it in iOS XR. And you have your /30 subnets that you're learning throughout the VRF. Okay. Interestingly, in iOS XR, it tells you the protocol next hop right there in the per client rib, in the VRF rib. So you don't have to dig any further. Let's look closer at the route reflectors in Junos router 3. If we show route table, we do not have a VRF table because router 3 does not have a customer hanging off of it. There's no customer here. Therefore, we don't have to have a VRF IPv4 table, but we do have a BGP L3 VPN table, which is part of the route reflector activity. So if we look at that, we see that for every /30 that is learned in the VRF, we have an entry in there, but it looks a little strange. This is because this is the preceding 64-bit route distinguisher for this VPN v4 address. So the 64-bit route distinguisher plus the 32-bit IPv4 prefix forms the 96-bit VPN v4 address. And so this is very nice. In the route reflector, we can see exactly where it's learned, .1, .2, .4, .5, and .7. Let's look in iOS XR. Show route VRF. There is no VRF. If we say all, there's none there. And this is because router 6, likewise as router 3, does not have a customer hanging off of it. So we don't need a VRF table to be a route reflector. But what we do have is a BGP table. And what we see there is we have the route distinguisher and the IPv4 prefix that we're learning from that route distinguisher. So from 10.10.01, we're learning this /30. .2, we're learning this one. From .4, we're learning this one. .5, this one. And .7, this one. Okay, let's talk about some redundancy aspects real quick. Remember I told you on router 1 PE that when we looked at the VRF table, the active path was from 10.10.03 for all of our VRF prefixes. So looking back at the two route reflector dual hub nodes, that router 3 and router 6, if we lose router 3, what happens to these active paths and what kind of impact does the customer feel? Well, let's look at that. Let's go back over to router customer edge 1 and let's ping 192.168.1.6. Here's router 1. 192.168.1.6 is CE3 clear across the network. So let's start pinging that. Let's go back to router 3 and let's show configuration protocol, BGP. Let's go into config mode. Let's delete protocol BGP completely. Show pipe compare shows our pending change. Look at all of those minus signs beside all of our neighbors. So we're about to get rid of the entire BGP process. Let's commit this. Now, let me pipe grep from, so we see all these prefixes are from 10.10.03. There's our pings. Let's commit this. Let's watch the pings. I don't see any ping drops yet. Let's go. Let's move this out of the way. Those pings are still flowing. Let's hit the up arrow on this. Now look at that from 10.10.06. So 10.10.06 is our other route reflector of the dual hub architecture. So that stuff failed over so quickly that the pings didn't even drop, as we could see there. Let's restore this router. Rollback 1, show pipe compare, shows our pending change. There's our plus signs. We're about to roll back that BGP configuration. Run, let's just look real quick. Run show BGP summary. BGP is not even running. It's gone. Let's bring that back. Let's watch these pings. Let's look at router 1 here. Those pings are still running. Let's see if router 3's sessions come back up. They're active. They're not up yet. Let's keep watching those pings. Some of them are coming established. Let's wait till it's done. Those pings are still rolling. Some are established. Open sent. They're all established. The pings keep going. Let's go back over here. And there you have it. We are back on the active, original active path. Oh, that one's still 10.6. It's still converging. Okay, they're all on 10.10.03. We never dropped a ping. It's a beautiful thing. So the redundancy aspects of a dual route reflector hub are great. As you could see, you could bring down one of your route reflector nodes, and those routes are still learned over that other active node. Hey, that's all I got for you. If you like what you're getting from this channel, go ahead and subscribe.